Get started. So Ohm's law. We were also having this discussion before the meeting started. About how physics, you guys, like in general, all of this stuff that we've been learning, it is practical, right? It actually does apply to your real life. And if you were here, that would have been even more obvious, right? Instead of having Mr. Hammond or I talk to you all the time. But this section of physics is probably the one that you'll experience the most in your lives, right? It's like the quote-unquote most practical. And actually, I usually tell students that if you want to get a high-paying job that's going to not break down your body a lot, like becoming an electrician, actually getting to know all this stuff in depth and understanding it and becoming an electrician, that's a great job, right? A union electrician usually starts around 60K if they're a journeyman. So, and then it goes up, up, up. And when I say you don't break down your body, it's not like being a construction worker where you're doing heavy work all the time, right? So anyway, this stuff is useful, right? It is. So Ohm's law. Obviously it's named after a person. Let's talk about what it is. It's really, Ohm's law explores the relationship between voltage, current, and resistance. So remember, this is from yesterday, right? Let's just do a little bit of review from yesterday. Voltage, that's the difference in energy between any 2 points in the circuit, okay? It's also called the potential difference because it's the difference in potential energy is what it is. And remember, we talked about this before, the difference in energy is also called what? Starts with a W? Yeah, work, right? So the voltage actually, when you measure it, what you're really measuring is the amount of work done in the circuit, right? The amount of energy that's used up. Now that energy difference is actually also causing the pressure. So it's causing the push. It's pushing the electrons through the circuit. Resistance, that's how hard or how easy it is for the electrons to move through the surface. So if I have a wire made out of copper, the electrons move really easily, right? If I have a wire made out of plastic, that's not going to work so well because the electrons don't move so easily. And then finally, I have current. And current is the amount of electrons that are moving through a point in the circuit at any one time. So the more electrons that are moving through, the higher the current. The fewer the electrons that are moving through, the lower the current. So we have the voltage, the resistance, and the current. And then remember that the voltage is measured in volts. The current is measured in amps. And the resistance is measured in ohms. So we named it after Ohm. I don't know if he was a difficult person. Maybe that's why they did it. He offered lots of resistance. So good? This is from yesterday? Okay, a little bit of review. Okay, so now this is the picture that I kept showing you yesterday. It's kind of showing what the relationship is between voltage, current, and resistance. So this little guy right here represents the current. He's labeled with amps. This guy pushing him, that represents the voltage. He's labeled volts. And then this guy kind of tightening the tunnel there, he's the resistance. So he's labeled ohms. So in this case, in this picture, the resistance is increasing, right? Because he's making it harder for him to get through. And then the voltage, that, remember I told you that's the analogous to the pressure. So he's trying to push the electrons through. So what is the relationship, say, between current and resistance? So I'm gonna pick someone at home Axel, what's the relationship between resistance and current? This guy and this guy. Axel, are you there?
Yeah.
So what do you think the relationship is?
I think that they're trying to like get him through, right? They're like both trying to.
Well, yeah, so we're not going to look at the volts. We're just going to look at the ohms and the amps. So if the ohms, it represents the resistance, right? The amps is the current. So if the resistance gets higher, meaning he tightens this up, what happens to the current?
Doesn't it get quicker to try to push him through more?
Well, so I want you to think. I want you to think about, say, the hallway at Leiden. So there are some hallways at Leiden that are really wide. There are some that are narrow. And if I narrow the hallway, that would be increasing the resistance, right? So if I have a really wide hallway, I got lots of people walking through there, what happens? So at the beginning of school, everybody comes in the back entrance by the PE, right, area, and then you turn right, and you're walking down that 060 hallway towards the inner core, right, towards the Eagle. What happens when you hit those steps at the end?
You slow down.
Yeah, you slow down, right? So that would represent the current. If you slow down, there's fewer people walking through a point at any one time, right? So if the resistance goes up or the hallway narrows, then the current goes
slower.
Yeah, it goes down, right. Thanks, Axel. So then, it won't let Cindy in. Okay. All right, so then, Angel, this one's for you. If I increase the voltage or I increase the push, what does that do to the current?
Wouldn't it go faster because you're increasing it?
Yeah, that's right. So if I increase the push, then it goes faster. So this is basically what Ohm's law says. You guys just figured out Ohm's law, right? As the resistance increases, the current decreases. So as resistance goes up, current goes down. And then as the voltage increases, the current also increases. So that is Ohm's law. Now, because we love SAT, right, and we're thinking about all those graphs on the SAT exam, if I were to graph this relationship right here, do you remember what the graph looks like? Like, do you remember, Mark? No? So I'm going to graph this resistance. We'll label this as resistance versus current. Remember, if one thing gets bigger while the other thing gets smaller, that's called inversely proportional, right? And if it's inversely proportional, then the graph looks like that. So when resistance is big, current is little. When resistance is little, current is big. So Milena can verify. Wait, you did take it in fall, right? The SAT? Oh, you took it last year? Oh, okay. You can verify there's this graphing stuff on there, right? Like, this isn't something I just made up, right? It's on there. They'll give you like the data, or they'll give you the relationship, and you got to pick the graph. And then you guys, this one, voltage and current. Oops. So if I were to graph voltage and current, that graph would look like this, because as voltage increases, current increases. That's directly proportional. Okay. So you know, in physics, normally we don't write things out in words. We usually like to have equations, right, to show the relationship. So can I show you the equation that matches this? Okay. So basically the equation that matches this, you guys, the way to state this mathematically is that voltage equals current times resistance. That is Ohm's law, mathematically stated. So write that, you can write this on your equation list. Write it with all your other equations. And this is how we would write it out. Voltage, the symbol for voltage is a V. The symbol for current is not C, it's I. So current is a capital I, and then resistance is an R. So V equals IR, which is voltage equals current times resistance. Where remember our units, voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. And the symbol for volts is a little v, like that. Symbol for amps is an A. And remember, the symbol for ohms is a Greek letter omega. Looks like a horseshoe. So voltage is current times resistance. So if you look at this equation, right, if I keep voltage constant, if I keep that the same, the only way that this would work is that if the current went up, the resistance would have to go down. Or if the current went down, resistance would have to go up. You guys see that? So that's that inversely proportional relationship. And then if I keep resistance the same, so like let's say I have the same light bulb plugged into a flashlight, but I add extra batteries. Instead of just one AA, I have two AA's or whatever. So if the voltage goes up, the current goes up. Like it has to, right? Or if the current goes down, the voltage would have to go down to make that happen. Good so far? Still good? It's not super hard, right? Okay. So let's look at how this is applied, right? Let's do a problem. So my first problem, I have a light bulb, and the light bulb is put in a circuit with a 1.5 volt battery. Now, just so you guys know, that's a AA battery. AA batteries are 1.5 volts. Okay, and that's basically supplying 1.5 volts of energy from one end to the other end of the battery. Right? That's the difference in energy between the two, the positive side and the negative side of the battery. So I want to know, what will the current be in this circuit? Right? Now, this is something I'm going to stress at the end again. But you guys, for the battery, the electrons won't leave the battery and go through the circuit unless they have a route to go all the way back home. All right? So they won't leave the battery unless they can get back to the battery. Right? Won't go home. They won't leave home unless they can get back home. It's another way of thinking about it. So if they leave the circuit here, there has to be a wire that connects it to the light bulb, and then that wire has to continue from the light bulb back into the negative. If that circuit is broken in any one spot, it just won't work, right? It won't turn on. That's what switches are, actually. So a switch, when you turn it on and off, you're breaking the circuit and then reconnecting it, breaking it, reconnecting it. So you're taking like a wire out. All right, so let's write down what we know. So we know the voltage. Voltage is 1.5. Okay. I know the resistance of the light bulb, and the resistance is 5 ohms. Now those numbers didn't come from nowhere, you guys. A typical flashlight battery, if it's not an LED, right, an old school incandescent one, they're roughly 5 ohms. They're anywhere from like 2.5 to 6 ohms. All right? And I want to know, what is the current flowing through that circuit? So I would plug this in. I have one equation that has voltage, current, resistance, one we just learned, Ohm's law. And I'll put in 1.5 for volts. And that equals the current times 5 ohms. Oscar, you know, how do I get rid of the 5? What? Well, it's being multiplied, so I would do the opposite, which is divide. Yeah. You knew that. So I'm going to divide both sides by 5. Those cancel. And the answer is 1.5 divided by 5, which is, I don't have a calculator. Can someone at home help us out? What is it? Point 3. Oh yeah, I should have known that. Thanks, Melina. 0.3 amps. So that's relatively small current. This is why, like, if you have a little circuit with a AA battery and you hook a light bulb up to it, you can actually hold the light bulb with your fingers and you don't get a shock, right? Like, you don't feel it. The reason you don't feel it is because the current's pretty low, right? So can we do one more problem? Now the next problem is going to be almost exactly the same, except except we're going to change the voltage. So I have the same light bulb. I have the same light bulb hooked up. The resistance of the light bulb, 5 ohms. But now, instead of a battery, or instead of a flashlight that only has one AA, I have a flashlight that has 2 AA's. Right? I mean, everybody has put batteries in something, right? And most things require like 2 batteries, 3 batteries, 4 batteries. Now, just so you guys know, we haven't talked about this. We probably won't get a chance to. But if you hook batteries up in a series circuit like this, the voltage is add. So if I have 2 batteries in series, if they're both 1.5 volts, then it delivers 3 volts to the circuit. Okay? And they just don't make 3-volt batteries. So we have 2.5, 1.5. So anyway, now we increase the voltage to 3, and I want to know what is the new current. So I'll go here, and I have voltage equals current times resistance. Now, if what we said before is right, we said if the voltage goes up, the current should go up. So let's see if that was correct. So we have 3 volts equals current times 5 ohms. Oscar already told us that those are being multiplied, so I have to divide. Sorry. I'm not trying to get ahead of you guys. Sometimes I go too fast. So it's better when you're sitting in front of me. When people are sitting at home and they're just like doing the bobblehead thing, I don't know if they're actually like, just keep going or not. So then these are going to cancel. 3 divided by 5, I can do that math in my head, but you can confirm it for me. The current should be 0.6 amps. So I'm looking at everybody at home, making sure that, are you guys all good for me to, is that good? You got it written down? Yeah? Okay, good. So if we go back a slide, when the current was, when the voltage was 1.5, the current was 0.3. When I doubled the voltage to 3, I doubled the current to 0.6. So when voltage goes up, current goes up. Physics works, just the way I said it would. Now, normally I would make you guys actually do this and confirm it, but trust me, it works. Okay, can we do another problem? Now, this is going to be a variation on the exact same thing. Okay, so I'm going to have the exact same circuit with my 2 AA batteries. So my voltage, that's still 3 volts. But my light bulb burns out, and I look around my house, I have another light bulb, I take that one and I put it in. Now that light bulb that I put it in has a resistance of 10 ohms. What will the new current be, if that's the case? So in this problem, you guys, I'm going to go back really quick for 1 second. In the last problem, we had 3 volts with 5 ohms. now I have 3 volts with 10 ohms. So I doubled the resistance. So we only have one equation for this still, V equals IR. My voltage is 3 volts. Current, I don't know. Resistance is 10 ohms. And to get rid of the 10, we have to divide both sides. And 3 divided by 10, if you plug that in your calculator, it ends up being 0.3. So once again, the equation works the way that I said it would, right? I said if we increase the resistance, we should decrease the current. If you make it harder for the electrons to move, fewer of them can move. So when the resistance was 5, the current was 0.6. When the resistance is 10, when it's doubled, the current is only 0.3. Right? So far it's all working. Now this is why, and once again, this is one of the experiments we usually run in person. I have a simulation that we're going to try if we have time, like I said. But if I have a series circuit and I try to plug in more and more light bulbs, okay, you guys, what I do is I increase the resistance, which decreases the current. So the light bulbs actually get dimmer and dimmer and dimmer the more I try to plug in. And that's a series circuit. We're going to talk about this is when I only have one path for the electricity to travel through. Now, have you guys ever heard the term short circuit? Okay, like everybody's heard it, right? Does anybody know what that means actually? What a short circuit is? Yeah, that's exactly right. So I don't think you guys were able to hear that at home, but what Mark said is a short circuit happens when 2 wires actually touch each other. And what that does is it removes, like it would remove the light bulb from the circuit. Okay? When it removes the light bulb from the circuit, then the electricity runs out of the battery and it just goes through the wire and back in without actually having to power anything or leave its energy for the light bulb. This happens a lot, actually, in old cheap headphones, the wired ones. Like everybody's had this thing where the wires, like you have to move the wire for it to work, right? And because what's happening in there is the shielding for the wires is actually rubbed out, and the wires are touching each other. And so instead of the electricity going all the way up into the headphone like it's supposed to, it just goes up to the point where they're touching and then back into the battery, right? So let's see what happens when we have a short circuit. So this is my short circuit. I take out the light bulb, I replace it with a wire. Now, what's going to happen to this circuit? Well, I have the same circuit, so I have a voltage of 3 volts. But copper wire doesn't have a whole lot of resistance. It has 25 ohms of resistance actually for every 1,000 feet of 24 gauge copper wire. So if I just have a little circuit like in my flashlight, the resistance in that wire is just going to be 0.013 ohms. Once again, that's not a number I just pulled out of the air. That would be typical for, like 6 inches of wire, copper wire in this device. And then I want to know what is the current in that circuit. Well, voltage equals current times resistance. And so the voltage is 3 volts. Current, I don't know. The resistance is 0.013 ohms. Now that's math I can't do in my head. So someone's got to help me out. To get rid of the 0.013, I have to divide both sides by it. That cancels out. It's going to be big. 230 amps. Yeah. Seems crazy, right? Yeah, so I don't know if everybody heard what Mark just said. He's like, so it's going to melt. And that's exactly what happens. It heats up incredibly hot because there's so many electrons going through there. There's a lot of friction, and it'll just melt and kill the circuit. So that's what happens in a short circuit. If that were to happen in your house, and you didn't have a fuse, it would start a fire. I'm sure you've heard of electrical fires starting in people's houses, okay? But that's why you have that big fuse box downstairs, and it triggers the fuses. You have to move them back and forth. Does everybody know what I'm talking about? Right? In the old days, like I actually still had, when we moved into our house, I still had some that were screw fuses. They look like little light bulbs, and every time the fuse would blow, you'd have to take it out and actually replace it with a new one, just like a light bulb. And then it would be super frustrating because if whatever was causing the problem was still causing the problem, that would burn out too, and you'd have to buy another one and put it in. So our modern fuse box is so much nicer. But that's what happens in a short circuit. Now, I don't know if anybody's ever done this. Do not do this. Just for fun, right? Don't do this. But 9-volt batteries, and I meant to grab one before I came in. Everybody know what a 9-volt battery looks like? So 9-volt batteries are those little square ones. So they kind of look like this. And then they have the two posts. So there's like a post, and then there's like the receptacle post on the top. And you plug things into them. Now, the 9 volts always come. When you buy them at the store, there's always a piece of plastic that sits over the top of those two posts. And you're not supposed to take that off until you plug it in. Why? Because let's say that you took that off, and then you threw it, like, in your car, how you always have like that one thing in the middle, the center console, that you just throw your coins or whatever into. Like you get a few pennies at the drive-thru, you throw them in. Or if you throw that into that center console, and this is connected like by a copper penny, the electricity will run through this, and it'll explode. It'll heat up. You'll be getting hundreds of amps of current running through that. And it could actually start a fire as well. So you have to be really careful not to do things like that. So that's a short circuit. Now let's do one last problem. So I have a new circuit here. And in this circuit, the battery is 6 volts. The current is going to be 0.4 amps. And I want to know what the resistance is, since we solved for the same thing every time before. So let's just do something different. So in this one, voltage is 6. Current is 0.4. And then resistance is what we're trying to solve for. Now notice I changed the circuit a little bit, how I drew it. So instead of drawing it like a visual representation with a picture of a light bulb, when we do circuit diagrams, they look more like this. So if you ever pull out a circuit diagram for any piece of electronic equipment you have, it will look more like this than it will a picture of the actual insides, right? Where this would represent a load in the circuit or something that it's powering. That would be the light bulb. This represents a direct current battery. If it was an alternating current energy source, it would be a circle with a little wavy line inside of it. This is what switches would look like, right? So I flip the switch, I complete the circuit, I have a current of 0.4 amps running through it. What's the resistance? Well, voltage equals current times resistance. The voltage is 6 volts. Current is 0.4 amps. Then the resistance, once again, I mean, it's a pretty easy equation to use. I would just divide both sides by 0.4. And 6 divided by 0.4, 15? Yeah. 15 ohms. So, unfortunately, this is not a project we got to do, but last year we got to wire up like little signs with LEDs and stuff in them. And one of the things that you have to do, you guys, when you use LEDs, is you have to put a resistor in the circuit. And so depending on your power source, you have to calculate the resistance that you need to add into the circuit so that the LED doesn't blow out. And how would you do that? You just use Ohm's law, right? And then when circuits get a little more complicated, some parts of your circuit may need more resistance so that the components don't blow than others. So you have to, you have to figure that out and put it in the appropriate place. Good? Okay. So then let's talk just really quickly about what a series circuit is. And then tomorrow we're going to talk about parallel circuits and how Ohm's law applies. So a series circuit, you guys, is a circuit that only has one path for the electricity to travel through. If I look at this circuit, the electrons leave the battery. They go through this wire, right? When the switch is connected here, so the switch is open now, they won't leave, but if the switch is connected, those electrons will continue down the wire. They'll go through this first light bulb, through the second light bulb, around the corner, keep going, and then they go back home. So there's only one way that they can go. There's not alternate paths. If there was an alternate path, do you know what we would call that kind of circuit? Parallel, right? So parallel circuit offers alternate paths. Series circuit, it's just one path. So then, in a series circuit, because there is just this one path for the electricity, right? There's just the one way for it to go around. At any point in the circuit, the current is always the same. So if the current right here, say was 1 amp, then the current right here has to be 1 amp. They have to be equal to each other. The current in between these light bulbs has to be 1 amp. The current after that light bulb has to be 1 amp. The current going back into the battery has to be 1 amp. The reason for that is because if I have, let's say I have 100 electrons leave this battery, right? Well, those 100 electrons have to get back into the battery. They travel together, right? And if there's only one way for them to travel, then they're always going to be together. It's always going to be the same amount at any one point in the circuit. Okay? It's sort of like a river. If I have a river and there's no streams branching off, if there's only one channel for the water to go, then everywhere in that channel, it's going to have the same amount of water, right? Rivers only get bigger when there are streams feeding into them, adding more electrons. So I can't do that here. Does that make sense? So anywhere in a series circuit, current is always constant. But in a series circuit, the voltage changes. So remember, voltage is energy, right? So I close my switch. Let's say that this is a 6-volt battery. So the difference in energy from one end of the battery to the other end is 6 volts. Now let's say every one of these lamps is exactly the same. Every light is the same. What that means is that this light right here is going to use up 2 volts of the electricity. And this light right here, from here to here, that's going to use up 2 volts of the electricity. And then this light right here, that's going to use up 2 volts of the electricity, right? So when you measure voltage, you have to take your 2 probes and you have to put them on parts of the circuit that you want to measure the difference in energy of. So if I took my probes, if I took my voltmeter, and I put them right here, it would read 2 volts. Because that's how much voltage is getting used up. If I put them here, it would read 2 volts. If I put them here, it would read 6 volts. Because the difference in energy from the start of the battery to the end is 6. All of the voltage is getting used up. If I put one probe here and one probe here, what do you guys think it would read? 4 volts. So that's like another confusing part of electricity to a lot of people. Is that they think if they take like a voltmeter and they put it on the wires here, that it'll read 6. It won't. It'll actually read 0. Because the difference in energy that's getting used up in the wire itself is so small that it's 0. Because the wire is not really using up electricity, right? It is over the long haul, but not like in short distances. So that's how voltage works in a series circuit. And then resistance in a series circuit, it adds up. So like if this lamp was 1 ohm, and this lamp was 1 ohm, and this lamp was 1 ohm, then the battery would think that there was one 3 ohm lamp connected. So that's why the more lights that I put in this circuit, the higher, as far as the battery is concerned, the higher the resistance is, and the lower the current, so then the light bulbs won't get lit up as much. So there's a limit to how many things I can plug into a series circuit and still have them power up. Which is why in your house, we don't use, it's not wired all in series, right? It's wired in parallel, because in your house, if you plugged in too many things, they would all just stop working. But that doesn't happen, does it? So that's where I want to end today. That was a lot of info. Tomorrow we're going to talk more about parallel circuits.